Hi, I'm Carlton Coffrin, a staff scientist at Los Alamos National Laboratory, and in this presentation, I'll be telling you about some joint work with three of my collaborators, Yuchen Peng, Andrei Lakov, and Marc Fouffret. I'll begin by motivating with what I consider the holy grail of optimization on DWave. That would be you send an Ising model to the hardware, get a near optimal solution back much faster than any other solution method out there. Now, this statement is not particularly precise. We would have to flesh out the technical details of what does it mean to be near optimal, what is much faster, what are the other solution methods we're going to consider, and how many computational resources do they have access to. But the goal of this work is really striving to find a holy grail that would have these type of high-level properties. Now, seeking this holy grail is not for the faint of heart. For many of you who've used the 2000Q platform, you likely have realized there's a lot of constraints which make it difficult to encode and get high-quality solutions out of the hardware. First and foremost, it's a relatively small chip by optimization standards, although it's a very large chip by quantum computing standards. The graph it implements is relatively sparse. There's a fixed energy scale and effective temperature, and things like flux qubit noise can also have detrimental impacts on finding high-quality solutions. So in this work, we propose the Corrupted Biased Ferromagnet as a new class of Ising models designed specifically for benchmarking DWave and highlighting its strengths. I would like to emphasize this is not the Holy Grail. We believe it's a step in the right direction, but there's still work ongoing to really search for the true Holy Grail. And the punchline of this talk is that we'll show you that this instance has about 100x runtime advantage when running on DWave's 2000Q over HFS, which if you're familiar is a state-of-the-art heuristic that's often used for benchmarking DWave's performance on optimization problems. Let me tell you a little bit about the benchmarking approach because it might be relatively new. First off, what is the computational task we're interested in solving? We're going to be optimizing the classic Ising model with quadratic and linear interactions. On the DWave platform, you could consider generalizations of this, but this is the one we'll focus on for this work. We're also going to focus on what I would call DWave native problems. So these are problems that you can represent on your particular hardware graph without the need for embedding or any kind of logical transformation. So what we're going to do is we're going to take the DWave hardware graph, we're going to run a problem generation algorithm to generate different instances of Ising models on that graph, and then we're going to send those instances to the other competing algorithms and then back to the DWave platform to get results. These problem generation procedures are going to be stochastic or probabilistic. So what we'll do is generate 100 random cases and then present the mean value of all the algorithms across those cases to give kind of an average case performance trend. Now, what different types of solution methods are we going to consider? There's two big categories, complete search and local search. The complete search solvers provide global optimality proofs, so they have guaranteed convergence and can provide proofs of the correctness of the solution. We're going to check integer quadratic programming and integer linear programming. We also did local search heuristics, some based on Glover dynamics, some based on belief propagation, some basic greedy things. But the highlight here is a large neighborhood search algorithm called HFS, which is a state-of-the-art competitor for optimization on chimera graphs. And last but not least, we will also consider quantum annealing using LANL's DWave 2000Q chip. I've highlighted integer quadratic programming and large neighborhood search here because I would consider both of those to be state-of-the-art approaches, while the other approaches are more like straw men that we use to get a breadth and intuition for what might work or not work for solving different types of Ising models. In terms of an experimental design, we're going to give the classical algorithms one thread, and we're going to measure their wall clock time performance spanning 6 orders of magnitude, 1/100th of a second to 1,000 seconds. And then we'll ask them to give us the best solution that they can find in that given amount of time. For quantum annealing, we want to emulate this type of wall clock time limit, although it's not exactly obvious how you would set a wall clock time limit. So what we're going to do is set the annealing time to 5 microseconds, and then increase the number of reads we take from 10 to 20 all the way up to 10,000. And then of those reads, we'll return the highest quality solution we have in terms of energy. Now, I think there's two details to highlight. We didn't use any of the advanced features on the 2000Q platform, like annealing schedules or annealing offsets. Potentially those could significantly improve these results. And then in terms of the runtime we're going to report, we're going to do total real time as returned by the DWave server, which excludes communication and scheduling, which is roughly 1 to 2 seconds. But in principle, that could be removed through engineering effort. In terms of metrics, we're going to be showing you performance profile metrics, where the runtime of the algorithm is on the x-axis and the solution energy or the objective value is on the y-axis. So what you'll see is monotonically decreasing curves like this, which show you the energy of the best solution found for the amount of time that you have been given. There is a black line down at the bottom, which indicates the energy of the optimal solution. And then we're actually going to report the optimality gap, which is the relative difference between this optimal solution and the particular energy of a given solution, because this is problem agnostic. It doesn't have a particular energy value, it's just the relative difference. Now, one nice thing I would like to note about these particular performance profile metrics, and one of the reasons why I like to use them, is that by better engineering of your algorithms, you can make them run faster, which means that you can move this curve to the left. But you actually can't shift it down without a fundamental algorithmic change. So this is a very useful tool for myself, because when I see that it converges to a high quality solution eventually, I can measure how much faster it needs to get to match a certain performance. But if it never reaches a high quality energy, then I know there's no hope in this algorithm. I need to fundamentally change the algorithm to find a better solution. Now I'm going to motivate these particular metrics using a classical example, which is kind of a randomizing model with random fields. So let's consider this problem where we set the quadratic terms j to -1 and 1 with 50% probability, and we set the local field h to -1 and 1 with 50% probability each. This is kind of a totally random input to the DWave hardware. And this is motivated by spin glasses in Ising models, which are kind of known to have hard computational properties. In this evaluation study I did back in 2017, I evaluated a bunch of different instances that were available in the literature, and I found this one to be one of the most interesting from a benchmarking standpoint. Now, I'm just going to skip a lot of the details and zoom in on like the core result, which is a story that is known all too well by people who are benchmarking DWave and quantum annealing, which is the performance profile you see on the left here, where the orange line represents HFS, the local search heuristic, and the green line represents DWave. For most of the plot, the orange line is lower, which indicates that HFS has a performance advantage. And this leads many folks to conclude that HFS is faster than DWave. And for optimality gaps of 0.2%, that would be the case. Now, the claim I made in that previous paper, and also I've seen in many other instances, is that even if the DWave hardware does not find the true optimal solution, it usually gets very, very close to an optimal solution. So here you can see the relative optimality gap here is incredibly small. And for many practical purposes, there may be no distinguishing feature between 0.3% from an optimal solution and an optimal solution. So in our previous work, we proposed this was not an ideal case for benchmarking because this optimality gap was so small. So now I'll tell you a bit about this proposed corrupt biased ferromagnet instance, which we abbreviate CBFM. So on the hardware graph, you can see it on the right, it looks something like this. And the first thing to look at is the quadratic terms j. The j values are mostly -1, which is a ferromagnetic coupling in the DWave notation. And that encourages all the spins in the system to take the same value. So by and large, this is ferromagnetic, it's -1. But there's a small amount of corruption, which is about 1/3, where the value is 0.2. So this is the corrupt part of the biased corrupt ferromagnet. And this makes the problem somewhat tricky to solve, but also it doesn't lose this ferromagnetic property that links all the spins together. The second thing you can look at is these probabilities of the H values. So the H's are mostly 0, 97% of the time it's 0. But then on a rare event, there is going to be a -1 or a 1, and these are biased towards -1. So you have a 2% probability of getting -1 and a 1% probability of getting 1. So this biases the solution towards one particular side of a ferromagnet, which is all -1 or all 1. Now, in practice on the platform, we're going to apply a random gauge transform before we solve these problems. But for the purposes of this talk, I'm not showing that to you so that you can see the structure in these visualizations. Now, I'll draw this cartoon to try to give you an intuition for what the energy landscape of this corrupted biased ferromagnet looks like. You could think about all the assignments to the problem on the x-axis. It would be like 2 to the n assignments starting with 1, 1, 1, 1, 1, and ending with -1, 1, 1, 1, 1 on the right-hand side. And we know that at these two extremes, there are two wells in this problem, and they are separated by a very specific amount of energy, which is on average 0.01 times the number of spins in the system. So the energy landscape looks something like this, where there's a lot of ruggedness, but there are these two big wells on either side. And our hope is that some kind of a local search algorithm will start in a random place in the middle of this figure, and it will have some probability of falling into the wrong well, and then it'll be stuck there forever because it has to make an extremely large move to get to the other side. Where with quantum annealing, you would hope that superposition and other properties of the quantum system will allow you to avoid these issues and really see the two extreme wells and get the good one with a high probability. So if we look at the performance profiles for this CBFM result, you can see something that is very good news for benchmarking. So the first good news is that it's a relatively challenging problem for 5 of the 7 algorithms we considered. So if you look at the purple line, the light blue line, brown, red, dark blue, they're all well above zero optimality gap until a certain amount of time has passed. You can see the local search solvers tend to kind of plateau at a specific solution quality, while the complete search solvers slowly go down to zero optimality gap, and that's one of the big advantages of that algorithmic approach, is that you will reach zero optimality gap eventually. The very good news is that if you zoom in, you'll see this is still a challenging problem for HFS, although it's a fantastic heuristic, so it beats all the other ones, but it's still quite challenging. And then the very good news is that DWave on this instance is still performing very well. So let's zoom in and look at this particular subplot in more detail. So what you can see here is that the green line is strictly below the orange line, which indicates that for any amount of time budget that you have, DWave is going to outperform HFS. So quantum annealing is clearly the fastest. That's like a very great step towards the showing a significant performance gain for DWave and quantum annealing hardware. The first thing you can consider is kind of the y-axis of this plot. If you have very little time available to you, the question is how much quality gain will you get? And what you can see by the points I'm indicating here is that you'll get about a 2% improvement in solution quality. The next question you can ask yourself is, given that you want a particular solution quality, how much time do you save? And so by looking at slices on the x-axis, you can measure this. And just as a scale, I'll include in this logarithmic scale what 100x is, and that's this red indicator. So what you can see here with the red indicator is that you get roughly 100x runtime improvement for a given optimality gap when you use quantum annealing. Now, another question that you might be asking is what's going on down here, because for very small optimality gaps, all of the algorithms seem to be plateauing. To investigate that, we can plot that scale on the optimality gap on a logarithmic scale. And here I'm showing you this along with different measuring bars for the 100x improvement. And the good news here is that you can see for different levels of optimality gap, you still get about 100x improvement in runtime, which suggests a nice robustness property for different levels of solution quality, you still have a significant performance gain of quantum annealing over HFS. So now that we have a problem where DWave is producing high quality solutions very fast, we can start to think about hybrid solution methods for those types of problems. Now, there's a fundamental challenge with these heuristic algorithms, including quantum annealing, but also HFS and other local search methods, is that you don't know when to stop them. You run them for some amount of time, and you kind of hope you have a good solution, but you never know if it really is the best solution. So a benefit of the complete search algorithms like integer quadratic programming is they finish eventually. They're worst case exponential runtimes, but they provide a clear stopping criterion, and they provide an optimality proof at the end, which is valuable as well. So we can think of a fairly simple proof of concept hybrid algorithm where we could get the best of both worlds. First, we're going to collect 100 runs on our DWave computer, which takes about 0.2 seconds. And then we're going to use the best solution that came out of that hardware as a start for the complete search algorithm with the hope that it can improve it and eventually provide an optimality proof and terminate. So this is the performance profile zoomed in even further with the addition of this maroon hybrid algorithm that uses both DWave and Gurobi. And what you can see here is it does exhibit the features of both approaches. So for very small timescales, it's going to track the quantum annealing result because it just takes the solutions that come out of the hardware. And then for longer timescales, like on the order of 50 seconds or 60 seconds, it will provide an optimality proof and terminate accordingly. So I'll just finish up with some conclusions. That's the core results of the talk. Everything I've shown you here today is in a technical report on arXiv called The Rapid Solution Structure, the Potential of Quantum Annealing for Rapid Solution Structure Identification. And I skipped over a lot of additional interesting things that are in that paper. For example, that paper proposes Hamming distance as a novel metric that can be used to highlight the performance of quantum annealing. It really is less sensitive to energy scaling and small errors in the solution. And this is why we called that paper fast solution structure identification, because it kind of mitigates some of the problems with measuring energy as a metric. There's also a very nice methodological process in the paper where we build up the CBFM instance from biased ferromagnets and frustrated biased ferromagnets that can provide some insights into what features are required for Ising models to be challenging on a wide range of optimization algorithms. So I'll just finish up with that there is still much to do. The search for the holy grail on DWave benchmarking is still ongoing, but we hope that these corrupted biased ferromagnets provide a glimpse into the potential that the DWave platform can have for combinatorial optimization. And we're very much looking forward to doing similar benchmarks on the next generation chip. So thank you very much, and I hope you enjoyed this talk.